Time has always had this reputation for being the one grown-up in the room, the universal rule follower, the cosmic librarian who insists everything be filed in order. But the more we look at the universe, the more it becomes obvious that time is not the stern authority figure we once thought it was. If anything, time is the universe's resident prankster, speeding up here, dragging its feet there, stretching itself thin, like it is trying to butter toast with a single molecule of effort. The real shocker is that this is not some rare exception that only happens in science fiction stories. It is happening everywhere, all the time, including around you right now. Time is flexible, fidgety, and occasionally behaves like it showed up to work without caffeine. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. Most of us grow up with the idea that time ticks evenly, because that is the only version we ever personally experience. Our clocks never suddenly sprint ahead. Our watches do not fall asleep on the job. But that is only because we live in a cozy pocket of the universe where things are relatively calm. Space out there is chaotic, dramatic, and deeply emotional. It bends, curves, stretches, spins, and occasionally gets thrown around by massive objects that act like giant cosmic bullies. Time, being tightly connected to space, gets dragged along for the ride whether it wants to or not. It is like time is holding onto the universe's sleeve, shouting, "Slow down," or "Wait up," depending on what space is doing that day. Imagine for a moment that time is not a steady march, but a kind of cosmic river. For us, floating gently in our safe planetary neighborhood, the river feels smooth and predictable. But elsewhere in the universe, that river thunders across waterfalls, spins into whirlpools, or slows into swampy stillness. Time does not have a single speed. It adjusts itself to the local terrain of the universe, which means the universe is essentially running a wild obstacle course, and time is trying to keep its balance while narrating the entire journey. Once you accept that time behaves differently in different places, everything suddenly becomes more dramatic. For example, if your friend were standing near something incredibly massive, like a collapsed star, their time would be running at a totally different pace than yours. You could be aging gracefully, like a well-tended avocado, while they might be aging like a stubborn rock that refuses to change at all. That is not science fiction. That is the universe's actual rulebook. And the strangest part? The rulebook makes perfect sense once you learn that time is not a solo act. It is part of a duo, space and time, always together, constantly reshaping each other. But if time is so unpredictable, why does life here feel so normal? The answer is that Earth is a remarkably stable spot compared to some of the reality-bending environments scattered across the cosmos. Our planet has enough gravity to keep us grounded, literally, but not enough to twist time into a pretzel. It is strong enough to keep us orbiting the sun, but not strong enough to slow our hours into molasses. In short, Earth runs a pretty standard schedule, which is why our timekeepers can get away with updating atomic clocks instead of defending them from gravitational tantrums. Yet the idea that time is variable is not just a quirky cosmic footnote. It is a clue that the universe is far stranger and more dynamic than the human brain initially assumes. It suggests distance might not be as straightforward as we think. It suggests clocks are not just ticking, they are negotiating. It suggests that two observers in different places might disagree not only about events, but about the very pace at which events unfold. Time's flexible behavior means the universe does not offer a single rhythm. It offers billions of local rhythms, each one shaped by the neighborhood around it. This becomes an almost emotional realization. The universe has never been synchronized. Every corner of it is living on its own schedule, like a cosmic family that refuses to agree on when dinner starts. Time zones on Earth? Child's play. The universe has time versions, thousands of them, stacked across light years. It is enough to make you wonder if time even knows what it wants. One galaxy's second could be subtly out of step with another galaxy's second, and none of them are wrong. They are simply responding to their environment. So as we begin this journey into why time runs at different speeds across the universe, keep in mind that your intuition is probably lying to you. The clock on your wall is unaware of how rebellious time can be once it leaves home. The steady rhythm you trust is only the universe being polite. Beyond our comforting little bubble, time is stretching, bending, slowing, sprinting, and occasionally doing the cosmic equivalent of tripping over its own shoelaces. And the more we understand that, the closer we get to understanding the universe itself, not as a quiet, orderly place, but as a wild landscape where even time refuses to behave. If you have ever tugged too hard on a sweater and watched it warp into a lopsided rectangle, you already understand the universe better than you think. Because at its core, the universe operates on a fabric of its own, something far stranger and more elegant than cotton or wool. This fabric is called space-time, a four-dimensional tapestry where every thread of space is intertwined with a thread of time. You cannot pick apart the weave. You cannot yank one thread without the others twitching. Space and time are permanently married, occasionally bickering, but mostly functioning as a single, inseparable structure that holds reality together. The idea of space-time can feel slippery at first because our senses are not built to detect it. We can see space. We can feel time passing every time we remember that we left laundry in the washer 3 days ago. But we cannot directly perceive how they blend. Yet the universe does not care what we perceive. It only cares how things actually work. And what actually works is that space and time are locked together in a cosmic duet that choreographs everything from falling apples to drifting galaxies. To wrap your mind around this, imagine that space-time is a giant, stretchy stage on which everything in the universe performs. Planets, light beams, atoms, you, everything dances across this stage. But here is the key. The stage is not a rigid platform. It flexes, it bends, it stretches like the world's most dramatic trampoline. And because time is fused into that stage, whenever the fabric of space gets distorted, time itself gets dragged along for the ride. It is as if time is saying, well, if space is leaning that way, I guess I am leaning too. One of the most surprising things about this fabric is just how pliable it is. The slightest nudge from something massive, like a star, a planet, or even a cluster of wandering dark matter, can cause space-time to dip or curve. The bigger the mass, the deeper the dip. Picture a bowling ball dropped onto a bedsheet. The sheet stretches downward, forming a little pit around the ball. Now imagine tossing a marble nearby. The marble rolls toward the bowling ball, not because the bowling ball pulls it, but because the sheet tells the marble, this is the curved path now. That sheet is space-time, and the marble is anything that moves within it. But here's where the story gets wonderfully weird. Time also flows differently depending on how that sheet bends. In the curved parts of the sheet, the tempo of time stretches out. In the flatter parts, time runs at its usual pace. That means the ticking of time is not universal. It is local, shaped by how tightly or loosely space-time is wound in the region you are standing in. If space gets squeezed, time changes its rhythm. If space gets stretched, time sighs dramatically and takes its sweet time to move forward. To understand why, it helps to picture space-time not just as a fabric, but as a fabric under tension. In areas where space-time is stretched thin, time moves more quickly because it is not dealing with much resistance. It has room to stride freely, like someone walking through an uncrowded hallway. But in places where space-time is compressed or warped downward by something massive, time gets stuck in a cosmic traffic jam. It slows because the structure of space-time forces it to move through a thicker, more distorted region. It is like trying to sprint through waist-deep mud. You can try, but time will simply laugh and say, "Nope, not happening." This stretching and squeezing does not only shape how time flows, it shapes how everything moves. Light beams bend gracefully around heavy objects. Planets trace curved orbits, not because they are leashed, but because space-time curves beneath them like a bowl guiding marbles. Even the straightest line you can imagine becomes a curved path in warped space-time. And every curve, every dip, every fold in this fabric quietly influences the rate at which time ticks. One of the most striking aspects of space-time is how democratic it is. It does not have favorites. Anything with mass or energy gets to leave fingerprints on the cosmic fabric. A small asteroid makes a tiny dimple. A star makes a much deeper, grander swoop. A black hole. That is space-time throwing in the towel and saying, "I give up, do whatever you want." And because time is woven into this fabric, every one of these dents and curves corresponds to a slight adjustment in the local tempo of time. It is almost poetic. The universe does not measure time with a universal metronome. It measures it with geometry. Wherever space-time bends, time becomes part of that shape. It slouches and stretches with the same laziness or enthusiasm as the fabric itself. This is why two observers, standing in two different gravitational landscapes, will not agree on how much time has passed. Their clocks follow the rules of their local patch of fabric, and no amount of arguing or comparing watches can change that. Space-time is, in the end, the great puppeteer. It pulls invisible strings that guide the paths of planets and the pace of time. It decides how fast moments unfurl and how objects drift across the universe. The more we understand the way space and time weave themselves into a single flexible fabric, the closer we come to seeing reality not as a collection of isolated pieces, but as one vast, interconnected structure, one that ripples and folds and stretches, shaping time with every movement. If gravity had a personality, it would be that friend who insists on hugging you just a little too long. Not in a creepy way, more in a "you are not going anywhere" kind of way. Gravity's grip shapes the movements of planets and moons, but it also does something far stranger, something almost sneaky. It changes how time itself behaves. To understand this, imagine time as a traveler trying to walk forward. Gravity is the enthusiastic fan blocking the hallway, slowing the traveler down without even apologizing. You might think time is above such drama. Surely time, the grand overseer of history, does not get slowed down by something as ordinary as gravity. But it does. The stronger the gravity in an area, the more sluggish time becomes. A clock resting near something massive, like a planet or a star, ticks more slowly than an identical clock placed farther away. It is not broken, it is simply obeying the local rules. And the closer that clock creeps toward a powerful gravitational source, the more it feels like it is wading through invisible molasses. To picture this in a story-like way, imagine a group of identical clocks, all eager to start a race. They stand at different distances from a giant brooding object, let us say a massive sphere floating in space. The clock farthest from the sphere stretches its gears and says, "Let's do this," ticking away with crisp confidence. But the clock closest to the sphere tries to move its hands and instantly feels a sense of cosmic exhaustion. It still works. It is simply operating in a neighborhood where time has decided to crawl. If you could hear the clocks, the distant one would sound like a crisp drumbeat, while the close one would mumble each tick as if it had just pulled an all-nighter. This effect is not a strange trick of machinery. It happens to anything that experiences time, whether it is a clock, a human brain, or the decay rate of a subatomic particle. Time itself genuinely slows down under stronger gravity, and there is no way around it. This is why two observers in different gravitational environments will live through different amounts of time, even if they swear they were together only moments ago. Gravity shapes time the way a slow internet connection shapes your patience, with quiet, inevitable interference. To make this more personal, imagine standing on a mountaintop while your twin stays at sea level. The twin at sea level is deeper in Earth's gravitational grip. Their moments stretch slightly longer than yours. That difference is tiny, but it is real. If you both compared lifetimes down to the tiniest sliver of a moment, you would turn out slightly older only because you lived where gravity tugged on time a little less. It is the universe's gentlest version of location, location, location. Now zoom out from Earth and picture an object so massive that it twists every rule into a new shape. Near such an object, time slows dramatically, like a narrator pausing before revealing a major plot twist. Stars and planets experience this. Even light passing close to a massive object becomes part of this decelerated neighborhood, its journey stretched into a slightly different rhythm of existence. A photon racing through strong gravity moves through time that is, in a sense, thicker. All of this leads to a surprising truth. Living near something heavy means living with time that drags its feet. But what does near mean in a place as vast as the universe? Near does not necessarily imply being right on the surface of something. Even hovering at a respectful distance from a very dense object, like a collapsed star, can change time significantly. A spacecraft that makes a close observation pass around a massive remnant could return home having experienced fewer moments than those who patiently waited for it to come back. Not because of speed, not because of malfunction, but because the craft dipped into a region where gravity held time hostage. But the strangest part of all this is that no one inside a strong gravitational field ever notices anything unusual. You never feel time slowing down for you. Your heartbeat still beats in its usual rhythm. Your thoughts travel in familiar pacing. A clock resting next to you seems perfectly normal. And that is because you are inside the same slowed flow of time as everything else in your environment. It is only when you compare your experience to someone who stayed farther from the gravitational source that the difference becomes obvious. It is like two people watching the same movie on screens with different refresh rates. Neither one can tell their own screen is different, but each sees the other's screen behaving strangely. Gravity's influence on time is not a small side detail of the universe. It is one of its quiet governing principles. The more massive the object, the more assertive gravity becomes, and the more time adjusts its speed to accommodate it. The universe is full of invisible hierarchies where time flows just a little differently from one location to another. Strong gravity zones are like cosmic bottlenecks where everything must inch along. Far from mass, time loosens up and strolls freely. The universe does not run on a single timeline. It runs on countless local timelines, all shaped by gravity's unapologetic grip. And the deeper you stand inside that grip, the slower your moments unfold, proof that even time bows its head when gravity leans in a little too close. Speed has a strange relationship with time, almost like an inside joke the universe has been laughing at since the beginning. The faster something moves, the slower time passes for it. It sounds backward at first. Surely racing through space should make time fly, not drag. But in the strange logic of the cosmos, high velocity turns time into a stubborn sloth. Move fast enough, and you can practically cheat your way into a longer youth, as if the universe is slipping you a secret loyalty card that says, "Congratulations, you now qualify for reduced aging. Enjoy responsibly." To understand why speed tampers with time, imagine that time is not a rigid conveyor belt, but a flexible walkway that responds to your movement. When you stroll casually, time keeps pace with you, unbothered, humming its usual tune. But when you start sprinting, really sprinting, at speeds that would make even light do a double take, time begins to stretch and thin out behind you. It resists, it slows, it acts as though it is clinging to your heels, trying to tug you back into the slow-moving part of the universe where everyone else comfortably lives. This effect, often called time dilation, becomes noticeable only when speeds soar to enormous fractions of the speed of light. If you drove a car around the block at your most reckless speed, time would not slow for you at all. But imagine a spacecraft accelerating to outrageous cosmic velocity, zipping through space at a pace that makes starlight seem sluggish. Inside that craft, time crawls more slowly than it does for someone back home. Every second aboard the ship stretches ever so slightly longer, like taffy being pulled by invisible cosmic fingers. Picture two friends. One stays on Earth, living a routine life with grocery lists and laundry days, while the other rockets into space at tremendous speed. If the traveler returns after what feels like a short trip, they may find that Earth has leapt far ahead in time. Maybe their friend has aged decades while they barely collected a handful of new wrinkles. It would be the ultimate, wait, what year is it? Moment. The traveler would not feel strange. They would not sense that their time was slowed. But side by side, the difference would be unmistakable. Speed, quietly and faithfully, altered the flow of their personal timeline. But why does the universe behave this way? Why does it reward high velocity with a slower personal clock, as if motion earns you a discount on aging? The answer begins with the idea that the universe enforces a strict speed limit. Nothing can move faster than light, not because the universe is picky, but because this limit keeps reality working. When something begins approaching this limit, time adjusts itself to protect that rule. Instead of allowing speed to grow unchecked, the universe stretches time for the object, making further acceleration increasingly demanding. Time slows for the traveler as a kind of cosmic safeguard, a graceful way of saying, you can move fast, but we're going to make sure you do not break the system. You can imagine this by picturing a runner trying to break the world speed record in a corridor full of moving walkways. At first, the walkways help, then they start moving backward, then they slow the runner down. Time behaves like those walkways, shifting in response to motion. The faster the runner pushes, the more the walkways change to ensure no laws are broken. The runner keeps moving forward in space, but time slides backward under their feet, moderating their personal pace. For the traveler, nothing feels different. Their heartbeat still taps along in familiar rhythms. Their thoughts unfold smoothly. They do not suddenly find themselves living in slow motion like a dramatic scene in a blockbuster movie. Instead, their entire experience of time stretches uniformly. Only when comparing their experience to someone else's do the discrepancies appear. Time dilation is polite that way. It does not interrupt the traveler's day. It simply rewrites the length of those days relative to the rest of the universe. Speed's effect on time also leads to some unusual possibilities when imagining life forms adapted to extreme velocities. A creature evolving in an environment where fast motion is the norm might live through long, stretched moments that feel luxurious and slow. A civilization capable of building near light-speed ships could witness entire eras pass by in distant parts of the cosmos while living through something as small as a single lifetime. Fast travel becomes a kind of time tourism, where the price for seeing faraway futures is letting the world back home age faster than you. But what really makes high-speed time dilation remarkable is that it shows time is not fixed. It is flexible. It adapts to motion with a precision that reveals just how interconnected everything is. Space and time are not separate rules. They are cooperative ones, adjusting themselves to maintain harmony in a universe that refuses to let anything outrun light or outmaneuver physics. The faster you move, the stronger that cooperation becomes. Ultimately, speed slows time because the universe is built on balance between motion and time, between the limits of energy and the structure of space-time. When you try to race across that balance, time steps in like a cosmic referee, blowing the whistle and adjusting the game so everything stays fair. You may not notice the change, but the universe does, and in that adjustment lies one of the most beautiful truths about reality, that time is not a metronome ticking in the background, but a fluid companion that shifts its pace in response to how boldly we move through the cosmos. If astronauts kept a diary, the strangest thing about it would not be the floating pens or the breakfasts squeezed from metallic pouches. The strangest part would be that their diaries quietly drift out of sync with the diaries of everyone back home. It would not be dramatic, no page stamped with "Welcome to the future," but with enough time and enough orbits, a subtle difference grows between the moments they live and the moments unfolding on Earth. Not because astronauts think differently, or because space does something mystical to clocks, but because relativity slowly rewrites the pace of their days. Imagine an astronaut preparing for a routine mission aboard an orbiting station. They wave goodbye, climb into a rocket, and blast upward through narrowing layers of atmosphere. As the engines roar and the planet shrinks beneath them, time begins its quiet editing. Their body does not sense anything unusual. Their pulse does not suddenly sync with a slower beat. Their thoughts do not elongate like a stretched-out melody. But in the background, the tempo of their personal timeline shifts ever so slightly away from Earth's rhythm. What makes this shift so gentle and yet so inevitable is the unique environment astronauts live in. High above Earth, they circle the planet at incredible speeds, moving quickly enough to feel the tug of motion on time. At the same time, they are also farther from Earth's gravitational center than the people walking on sidewalks or sitting in classrooms. That distance means gravity has a weaker hold on them, something they cannot feel, but time can. The clocks strapped to the station walls begin ticking at a rate just a little different from their matching twins on Earth. Now picture two identical watches, synchronized perfectly before launch. One stays on an earthly nightstand, ticking away calmly. The other follows the astronaut into orbit. After days or weeks of circling the planet, the two watches are no longer in perfect agreement. They have drifted. Their ticks have disagreed by fractions of seconds. This difference may seem microscopic, but in science, even a whisper of disagreement between clocks is a sign that something profound is happening. The universe is nudging each timepiece into obeying the laws of relativity. From the astronaut's perspective, nothing feels altered. They float from module to module, tether themselves for sleep, and watch Earth pass beneath them 16 times a day. But all the while, the universe is treating their experience of time differently than the experience of the family and friends who wave at the sky from below. The astronauts' fast motion nudges their time to slow. Their reduced connection to Earth's gravity nudges their time to speed up. Those two effects do not cancel. They interact in a gentle tug of war. Depending on the specific orbit and speed, one effect will win, leaving the astronauts' time running just a bit faster or slower than the time experienced on the ground. If this sounds like a cosmic glitch, it is anything but. Relativity is not just a theory scribbled on chalkboards. Mission Control has to account for these time differences constantly. Navigation systems depend on clocks so accurate that even tiny distortions could misalign an entire spacecraft. Engineers correct the timing of orbiting satellites because the universe insists on bending time around anything that moves fast or sits far from Earth's gravitational pull. Without those corrections, the calculations guiding spacecraft would slowly drift into nonsense, leaving astronauts on a joyride straight into navigational chaos. Time's flexibility might feel philosophical, but it is a very practical part of surviving spaceflight. The astronauts themselves live inside this altered flow of time without noticing a thing. They laugh at the same jokes, squabble over whose turn it is to clean the filters, and stare at the same sunrise cresting over Earth's horizon. But their lives are unfolding on a timeline nudged slightly out of step with the world below. When they return home, their age and Earth's age will still match closely, but not perfectly. They have lived moments that Earth has not. They have skipped moments that Earth has kept. They bring back the faintest hint of temporal misalignment, like a traveler returning from a trip to a city where clocks run a fraction faster or slower. These differences grow more dramatic as space travel becomes more ambitious. Imagine astronauts voyaging far beyond Earth's reach, gliding through interplanetary space where gravitational fields weaken even more. Their time would drift in ways that become measurable, even noticeable, once they return. A future crew sent to explore distant moons might come home to find that Earth has marched ahead a little farther than they expected, not because they traveled through wormholes or stepped into a science fiction plotline, but because time itself was quietly reshaped by the conditions of their voyage. Relativity is not merely a scientific idea. It is a lived experience for anyone who ventures beyond Earth's cradle. Astronauts become travelers in geography and travelers in time, carrying a story that the universe inscribes directly into the pace of their heartbeat and the ticking of their clocks. Their journeys teach us something unexpected. Time is not loyal to any one path. It bends to motion, responds to gravity, and shapes itself differently for every traveler. Earth may feel like the center of our timeline, but the universe insists otherwise. Each astronaut's mission becomes a gentle reminder that the flow of time is not one river, but a branching network of streams winding through the cosmos in ways we are only beginning to understand. Imagine taking a guided tour through the universe's most dramatic neighborhoods, places so intense, so gravitationally unhinged. The time itself stares blankly at the chaos and mutters, "I did not sign up for this." These are the domains of neutron stars and black holes, cosmic beasts whose gravity is so overwhelming that time does not just slow down, it practically forgets how to do its job. These environments treat time the way a malfunctioning elevator treats schedules. Everything gets delayed, nothing behaves normally, and anyone who steps inside might as well stop asking when they will get back. Let us begin with neutron stars, the leftover hearts of massive stars that once burned with glorious brightness. When such a star collapses, it crushes itself so tightly that its atoms buckle under the pressure. Electrons and protons squeeze together until they fuse into neutrons, creating an object so dense that a teaspoon of its material would outweigh mountains. A neutron star is the universe proving it can play the "how compact can I make this" game far better than any human engineer. Now imagine trying to stand near one. You would not be able to, of course. The gravitational pull is so mind-bendingly strong that even standing near it is a theoretical idea rather than a practical one. But if you could hover safely at a comfortable observation point, let us say tucked inside a magical spacecraft that is immune to destruction, you would witness something beautiful and bizarre. Time slowing to a crawl. Clocks near a neutron star do not tick. They drag their feet like exhausted backpackers trudging uphill. The monstrous gravity stretches space-time so deeply that moments around the star feel sticky, as though time has dipped itself in cosmic syrup. From your vantage point, you might try to send a message back to someone farther away, perhaps urging them to admire the strange flickers of light shimmering across the star's surface. But your message would seem delayed, not because the signal is weak, but because your definition of a moment has changed. Your seconds are longer now, stretched by intense gravity. Meanwhile, the person receiving your message sits in a region of gentler space-time where time moves briskly. To them, you sound like you are speaking through a slow-motion filter. To you, however, nothing feels out of the ordinary. You live inside the same slowed-down timeline, unaware that the universe is dragging your moments like heavy luggage. But neutron stars, incredible as they are only the opening act. The true headliners of distorted time are black holes, the most extreme gravitational phenomena the universe has ever invented. If gravity were a voice, black holes would scream. They are places where matter collapses into such compactness that space-time folds inward like a collapsing tent. Their gravitational pull is so powerful that not even light can escape once it crosses the event horizon, the invisible boundary that marks the point of no return. Approaching a black hole is like approaching the ultimate cosmic traffic jam. Every step closer slows time more dramatically until the seconds lengthen into minutes and the minutes threaten to become eternities. For a distant observer watching someone drift toward the event horizon, the scene becomes almost surreal. The traveler appears to slow down, then freeze, hovering at the border forever. Their movements stretch into infinity. Light from their body becomes dimmer and redder, stretched until it slips out of visibility. To the outside universe, the person has stopped existing in motion. They have become a permanent monument to gravitational stubbornness. But from the traveler's perspective, none of this feels strange. They feel themselves drifting forward smoothly. They do not feel time freezing. They do not feel their moments elongating. They experience only the steady, calm progression of their own personal timeline. And that contrast, time racing outwardly while slowing inwardly, is what makes black holes so astonishing. They create a disagreement between perspectives so vast that the universe must simply shrug and say, "Both of you are correct." Time becomes fractured, split by gravity's overwhelming grip. Move even closer, and the strangeness intensifies. Inside the event horizon, again, only hypothetically because no known physics allows you to survive this, you would encounter a realm where the directions of space and time warp into new meanings. The path forward becomes an unavoidable descent. The flow of time bends toward the center of the black hole like a river pulled toward a whirlpool. Even if you wanted to pause, you could not. You would be riding the greatest waterfall of space-time ever created, falling through distorted geometry where time is pulled inward with you. But the drama does not end there. Black holes can spin, twisting space-time around them like a cosmic whirlpool. They can drag entire regions of space-time into rotation. That means the very flow of time can become tangled, distorted, and looped. It is the universe's wildest ride, a place where time loses its composure and behaves like a confused traveler circling a roundabout. By the time our cosmic tour exits these extreme environments, one thing becomes unshakably clear. Gravity is not just a force. It is a sculptor that bends space, crushes matter, and tugs at time until time barely recognizes itself. Neutron stars slow it gently but relentlessly. Black holes crush it into near stillness. These environments reveal that time is not a fixed entity. It is reactive. It adapts. It becomes sluggish and distorted in the presence of overwhelming gravity. And somewhere in the quiet background of the universe, time probably whispers, "Next time, I want a vacation." If you have ever climbed a tall hill and felt proud of yourself, you can add another victory to the list. You were very slightly older at the top than you were at the bottom, and not because the climb felt like it shaved years off your enthusiasm for exercise. Time itself was running a microscopic bit faster for you once you reached higher ground. It is the universe's quiet reward for effort. No gold medal, no applause, just an extra sprinkling of moments handed out like cosmic confetti. And all of this happens because of something called gravitational potential, which sounds like a complicated equation wearing a lab coat, but is actually just a fancy way of describing how high up you are in a gravitational field. To understand gravitational potential, imagine gravity as a clingy friend who holds on to you politely at first, but becomes increasingly overbearing the closer you get. When you stand down near the center of that friend's gravitational attention, say at sea level on Earth, gravity's influence is strong. You are deep in gravity's personal bubble. But when you climb upward, away from the center of this gravitational enthusiasm, the grip relaxes. Gravity still cares, but in a more text me when you get home way, rather than a do not ever leave my sight way. Being higher up means being in a region where the universe is holding you less tightly, and that loosened grip gives time the freedom to move a little faster. The idea may sound strange because nothing in your daily life announces this shift. Your watch does not jump ahead when you reach the top of a tall building. A mountain does not brag about being a time accelerator. You do not hear mountaintop hikers shouting, "Behold, I age marginally faster." They would probably scare off the wildlife if they did. But the truth remains. Your location in a gravitational field changes the tempo of time. And that change comes from gravitational potential, the amount of energy needed to lift you, or anything, away from a massive object. Think of gravitational potential like climbing a cosmic staircase. The higher you climb, the more free you are from gravity's tug. Down at the bottom of the staircase, gravity keeps a firm hand on your shoulder. Up near the top, gravity takes a coffee break. When gravity's hold weakens, time becomes less strained. It leaps ahead with a bit more enthusiasm. The universe seems to say, "You made it up here. Enjoy this slightly quicker aging pace." But why does higher potential make time run faster? Picture time as a long-distance runner carrying a heavy backpack of gravitational influence. Down low, near the source of gravity, the backpack is packed full. Every step the runner takes is weighed down by the extra effort. Higher up, the backpack becomes lighter. The runner moves more freely. Time feels less resistance and can tick more quickly. Gravity does not just pull on objects, it pulls on time itself, slowing it down when its grip is tight. As you rise away from that grip, time sheds weight. This is why clocks positioned on satellites high above Earth tick slightly faster than clocks on the ground. They live in a region where gravitational potential is higher, where gravity's influence has relaxed compared to the planet's surface. Engineers must correct for this difference constantly, or the timing systems those satellites support would slowly drift off course. It is one of those details that sounds fictional until you realize it is quietly keeping your navigation apps from sending you into a lake. But the real charm of gravitational potential is how counterintuitive it feels. We are used to associating height with effort. Climbing stairs makes your knees complain. Hiking up a mountain makes your lungs reconsider their life choices. Yet in the physics of the universe, height means freedom. Freedom from the thick, slow-moving region of space-time that sits close to a massive object. Height means stepping into slightly quicker time, even if the price is an out-of-breath arrival at the top. If you want a story-like way to imagine this, picture the Earth surrounded by invisible horizontal layers, each one representing a different pace of time. Down near the bottom, the layers move slowly, like conveyor belts stuck in low gear. As you climb higher, onto rooftops, up mountains, into aircraft, you step onto layers that hum a bit faster. Stand just a few thousand meters above the ground, and you are already in a region where time slips by at a marginally brisker pace. Drift far enough away, perhaps into deep space, and you meet layers where time practically sprints in comparison to its pace down below. The difference is tiny, of course, so tiny that your birthday cake would not need extra candles just because you live on the second floor. But in physics, tiny differences are like whispered secrets with enormous implications. They show us that the universe is sensitive, responsive, and subtly layered. Time is not poured over the cosmos like syrup spread evenly across a pancake. It flows differently depending on elevation, bending itself around the landscape of gravitational potential. And the humorous part is that this means hikers, climbers, pilots, and anyone living in tall skyscrapers are racing ahead in time at a microscopic advantage. You could say people in penthouses are aging a little faster than those in basements. But do not worry, no one is gaining superpowers or losing years of life. The effect is far too faint to be dramatic. It is simply the universe reminding us that height, gravity, and time are all part of the same delicate dance. In the end, gravitational potential adds a charming twist to our understanding of time. Climbing higher lifts you into faster flowing moments, giving you a tiny head start in the cosmic race. It is a gentle, almost whimsical reminder that even the simplest act, standing a little further from the center of a planet, changes the tempo of your existence, proving once again that time is not just a passive backdrop to life, but an active participant, adjusting itself with the subtlety of a cosmic comedian delivering a deadpan punchline. If you have ever stood on a spinning playground merry-go-round, gripping the bars while the world blurred around you, you already have a faint hint of what rotating bodies do to time, minus the grass stains and the regret. In the universe, things that spin do not just twirl politely in space. They drag space-time along with them, tugging it, twisting it, and reshaping it into a slow swirl. Imagine space-time as a flexible sheet covered in invisible arrows showing the direction of time. Now picture a massive rotating object placed on that sheet. As it spins, the arrows bend and wrap around it, as if time itself has hopped onto a cosmic carnival ride and is being forced to circle endlessly. This effect, often nicknamed frame dragging, shows up wherever something massive rotates. And in the universe, many things rotate: planets, stars, collapsed remnants, and perhaps a few overachieving black holes that spin so fast they make washing machines look lazy. When such an object rotates, it does not simply spin inside space-time. It grabs space-time by the sleeves and insists that it spin too. The closer you get to the rotating body, the stronger this persuasion becomes, until time feels twisted into a circular path, like a dancer being pulled into a whirl. To imagine what this does to time, picture yourself floating near a massive spinning planet in a sturdy spacecraft. You hover at a safe distance, watching the clouds and storms swirl beneath you. You know the planet rotates, but what you cannot see directly is that the surrounding space-time is being pulled along. It is subtle, like a slow current in an otherwise calm lake. But this slow drag has consequences. Time in this swirling region behaves differently depending on whether you move with or against the twist. Move with the spin, and you find the flow of time becoming slightly more relaxed. Move against it, and time feels a little more burdened, as if you are swimming upstream against an invisible current. This asymmetry reveals a strange truth. Around a rotating body, there is no single universal direction in which time wants to flow. Instead, Time's pace and path depend on the cosmic swirl around you. It is as if the universe placed a giant roundabout ahead sign in space-time, and time has no choice but to follow the spiraling lanes. Now imagine drifting closer. The swirl tightens. The influence of rotation becomes stronger, not because the object is spinning faster as you approach, but because you are entering a region where space-time itself has become tangled. Here, time no longer prefers straight paths. It loops, it curves, it hints at directions that would make no sense in a normal environment. Every movement feels slightly tilted, like walking across a room where the floor itself is slowly rotating under your feet. If planets can produce this effect, stars can amplify it. Picture a star spinning with incredible speed, its mass enormous, its arms of plasma swaying like cosmic dancers. Around it, space-time becomes a lazy spiral that coaxes everything nearby to join the dance. Time is tugged along with a kind of gentle insistence. Particles moving in orbit around such a star follow paths that curve differently than those around a non-rotating object. Even light, which normally travels the universe with the arrogance of something that refuses to obey anyone, begins to bend its path more than usual in this swirling space. But the most dramatic example of all comes from rotating collapsed remnants, especially spinning black holes. These are the universe's champions of centrifugal drama. Their rotation is so intense that space-time gets dragged around them like a whirlpool pulling in the surface of the ocean. Where the swirl is strongest, the very meaning of direction becomes distorted. Try to hover still, and the rotating space-time nudges you forward. Try to move backward, and you fight a cosmic conveyor belt that insists you join the spin whether you want to or not. In these extreme regions, time behaves strangely. It can speed up or slow down depending on how you move relative to the swirl. Traveling with the spin, your moments can stretch slightly, as though time is easing its pace in sympathy with your direction. Traveling against it, your moments become more compressed, like a song forced into a faster tempo. A traveler circling a rotating black hole might find that the direction of orbit changes how time unfolds for them, giving space a personality that borders on mischievous. And yet, for all the cosmic chaos this creates, an observer inside the swirl feels nothing unusual. Their clocks tick normally. Their thoughts follow their ordinary rhythm. Even the swirl of space-time does not nudge their senses. It is only when comparing their experience to someone far away, from a region untouched by the spin, that time's distortion becomes clear. One traveler's minutes are slightly different from the others, and the cause is the universe's insistence on dragging space-time along whenever mass decides to rotate. This twisting of time has practical consequences too. Navigation systems orbiting rotating bodies must account for these small swirls, or their predictions drift subtly off course. Simulations of star systems hinge on understanding how rotation warps orbits. Even the behavior of jets of matter blasting out of spinning remnants depends on this dragged space-time, guiding them like rails formed by the twist. The whimsical part of all this is imagining time itself being yanked into a dance it never volunteered for. A spinning planet twirls, and time says, "All right, I guess we are doing this." A star spins faster, and time sighs. "Fine, I will swirl harder." A black hole spins at near cosmic limits, and time simply clings on, doing its best not to get motion sickness. In the end, rotating bodies reveal that time is not just something that flows through the universe. It is something the universe can grab, twist, and pull into motion. When mass spins, time does not remain aloof. It becomes part of the dance, circling in the wake of cosmic rotation like a passenger on a merry-go-round that never stops turning. If you have ever tried stretching a rubber band only to realize it stretches unevenly, tight in some places, loose in others, you have a decent metaphor for what the universe is doing on a grand scale. Space itself is expanding, pulling galaxies apart in a slow, relentless drift that makes even the most dedicated long-distance relationship seem manageable. But the real twist hiding inside this cosmic stretching is that it does more than separate objects. It quietly sculpts the flow of time. As space grows, it tugs on time like a mischievous child tugging on a tablecloth, slowly, subtly, but with effects that ripple farther than you might guess. The expansion of the universe is not something we feel in daily life. Our bodies are not stretching. Your coffee cup does not gradually widen while you drink from it. Even the solar system is blissfully unaware that space is stretching in distant regions. That is because gravity clumps matter tightly enough to resist the expansion on small scales. Expansion works its magic only in the vast, lonely reaches between galaxy clusters, where there is not enough gravity to hold everything snug. In these enormous cosmic deserts, space itself grows wider, carrying galaxies along like raisins drifting apart in an ever-rising loaf. Now imagine this expansion not as a surface stretching, but as the entire fabric of the universe growing roomier. When space stretches, time stretches alongside it, not literally as in minutes becoming rubbery, but in the sense that the expansion shapes how clocks behave across enormous distances. In regions where space is expanding more rapidly, time can drift at a slightly different tempo compared to regions where the expansion is calmer. It is like living in a house where the upstairs floor is slowly rising while the downstairs stays put. If you lived upstairs, your sense of height would gradually shift, even if you never noticed it happening moment to moment. One of the most surprising consequences of expansion is that distant galaxies live in a different temporal context than we do. Their light, traveling across billions of years, carries with it the imprint of a universe that was smaller, denser, and humming with a faster pace of physical processes. By the time that ancient light reaches us, space-time has stretched so much that the wavelengths themselves have elongated, as though the universe gently pulled them like taffy. If light can be stretched by cosmic expansion, you can imagine what happens to time woven into the same fabric. As the universe expands, the distances between galaxies grow, and the flow of time subtly shifts across those distances. Clocks in regions of space that have experienced greater expansion effectively tick differently than clocks in regions that have remained more gravitationally compact. Not wrong, not broken, just following local rules carved by the changing geometry of the universe. Think of it as neighborhoods forming their own timing traditions. Some celebrate the new year a split second earlier or later because their patch of space-time has stretched differently over cosmic history. This phenomenon becomes clearest when you consider how the universe looked long ago. In its youth, the cosmos was compressed and energetic, like a bustling city during rush hour. Time then flowed in a denser environment where light and matter collided constantly. But as the universe expanded and cooled, time began unfolding in a more relaxed setting. In a sense, the universe shifted from a frantic tempo to a more leisurely one. The cosmic expansion smoothed out density differences, giving time more room to breathe. Faraway galaxies still carry the signature of those earlier tempos within their ancient light, showing us glimpses of clocks that ticked at slightly different paces. But the expansion does more than shape the past. It influences the future. In vast regions of space, where matter thins out almost entirely, the continuing expansion means that time will progress at a pace increasingly detached from regions where galaxies remain clustered. Imagine two cosmic observers, one inside a tightly bound cluster of galaxies, another drifting in an immense void. The observer in the void experiences a space-time that is stretching more freely, while the cluster-bound observer lives in a region resisting the expansion due to its gravitational grip. Each environment molds the geometry of space-time, and in doing so, molds the tempo of time itself. This difference becomes even more interesting when you remember that the expansion of the universe is accelerating. Something, call it a mysterious pressure, a whispered cosmic nudge, pushes space to expand faster and faster. As this acceleration continues, distant regions of the universe drift away more rapidly, carrying their clocks into ever more distinct temporal neighborhoods. Over unimaginable epochs, entire sectors of the cosmos will become unreachable, their timelines diverging like branches on a tree that keep growing farther apart. And yet, if you lived inside any one of those regions, everything would feel perfectly normal. Time would flow as smoothly as always. You would celebrate birthdays, watch sunsets, and never suspect that your corner of the universe was gliding through a slightly different temporal rhythm than some faraway galaxy receding at fantastic speed. The differences would only show up through careful comparison, by examining light that has traveled across stretched out space, by measuring how cosmic radiation has cooled, or by noticing how the past and present align differently depending on where you stand. Cosmic expansion reminds us that time is not uniform across the universe. It is molded by the scale of space, shaped by how widely stretched space-time has become in each region. Time does not simply pass, it adapts to the size and tension of the cosmos itself. If gravity is the sculptor of local time, expansion is the grand designer of time across cosmic distances. Together, They weave a universe where every corner holds a slightly different rhythm. And somewhere, in the middle of this expanding tapestry, here we are, tiny observers trying to understand why time changes its tempo, while the universe quietly stretches everything outward like a slow-motion cosmic yoga session. If galaxies were people at a cosmic party, each one would arrive with its own personality, style, and deeply questionable sense of rhythm. Some would spin gracefully like ballroom dancers. Some would wobble like they are trying to remember the steps. Some would stand in the corner, quietly judging everyone else. But the one thing they all have in common is that they bend time in their own distinctive ways. A galaxy is not just a swirl of stars and gas. It is a massive, gravitationally sculpted environment where time meanders differently depending on where you stand inside it. In a galaxy, time is not a universal beat. It is a soundtrack remixed by gravity and geometry. To see how this works, imagine entering a large spiral galaxy, something majestic with sweeping arms that curl outward like frozen waves. Spiral galaxies are known for their elegance, but beneath that elegance is a gravitational structure more chaotic than it first appears. The densest regions are near the center, where stars pack together so tightly that their gravity forms a deep bowl in the fabric of space-time. The farther you move from the core, the shallower that bowl becomes. This creates a gradient, a slow shift in the way time flows across the galaxy. Down in the central region, time moves a little more reluctantly, nudged by the intense concentration of mass. Farther out in the spiral arms, where stars drift in looser communities, time strolls along with more energy, like someone who escaped a crowded room and finally has space to breathe. Imagine two travelers separated by tens of thousands of light years inside the same galaxy. One hovers near the galactic core, surrounded by the brilliant glow of densely packed stars. The other floats lazily along a spiral arm, far from the gravitational bustle of the center. They both carry identical clocks that were synchronized perfectly before they parted ways. After a while, the two meet again someplace neutral, perhaps drifting above the plane of the galaxy like cosmic tourists comparing souvenirs. And there it is. The clocks disagree. The one who stayed in the crowded central region has experienced time moving slightly more slowly. Their days were a bit longer, their seconds a bit more stretched. The traveler in the spiraling outskirts, meanwhile, lived through faster flowing moments without ever noticing anything unusual. Now shift your attention to elliptical galaxies, those smooth, egg-shaped collections of stars that look like the universe pressed the smudge tool across a cluster of light. Unlike spiral galaxies, these giants do not have arms or elaborate structures. Instead, their mass is spread more evenly, creating a gravitational environment that lacks the dramatic dips and gradients of spiral systems. You can picture an elliptical galaxy as a cosmic hill rather than a deep bowl with steep edges. The gravity is steady, strong, and widespread. Because of this, time within an elliptical galaxy tends to flow more uniformly. It does not fluctuate as much from one region to another because the galaxy does not have the stark contrasts between dense centers and sparse outskirts seen in spirals. But that does not make elliptical galaxies dull. In fact, some of the most massive galaxies in the universe are ellipticals. Immense lumbering giants stuffed with stars that have aged together like an ancient family reunion frozen in place. Their sheer mass can slow time significantly for anyone living within them. The difference between the time flow inside such a galaxy and the time flow in a smaller, lighter galaxy could be more dramatic than the difference between standing on Earth and hovering above it. Within an elliptical giant, every star, planet, and traveler experiences a slightly slower cosmic rhythm simply because the galaxy carries so much weight. Then there are irregular galaxies, the cosmic rebels that refuse to commit to any recognizable shape. These galaxies look as though someone tried to assemble a spiral but lost interest halfway through and decided to scatter stars randomly instead. Irregular galaxies lack symmetry, lack order, and lack anything resembling a standard gravitational blueprint. That means their gravitational fields are patchworks of stronger and weaker regions. Time in such galaxies behaves like a traveler wandering through a landscape where hills and valleys appear abruptly and unpredictably. One area might have a cluster of stars powerful enough to slow time noticeably, while another patch, just a few thousand light years away, might be so gentle gravitationally that time runs almost carefree. Living in such a galaxy would feel normal from the inside, of course, but if you traveled across it with precise instruments, you would witness the tempo of time shifting in irregular patterns. Now consider galaxies that interact or collide. When two galaxies pass near each other, their gravitational fields interlace like fingers, creating tangled webs of distortion. Stars get flung into elongated streams. Gas clouds twist into strange shapes, and time, patient, dutiful time, bends around the combined mass. In these chaotic regions, where two gravitational landscapes overlap, the flow of time can become subtly layered. One region might experience a deeper gravitational influence than another, even though they share the same cosmic event. For a traveler caught in the middle of such an encounter, time could feel entirely ordinary, yet their clock would whisper a story of moments stretched or compressed by the gravitational ballet unfolding around them. What emerges from this grand tour of galactic diversity is a simple truth. Galaxies sculpt time the same way landscapes sculpt rivers. In dense centers, time flows sluggishly. In spacious outskirts, it glides more easily. In uniform systems, it moves steadily. In chaotic ones, it wanders unpredictably. Time in the universe does not belong to a single rulebook. It obeys the gravitational personality of each galaxy. Every star system, every orbit, every stretch of interstellar space participates in its own localized rhythm. And so, the next time you imagine galaxies drifting across the cosmic void, do not picture them merely as collections of stars. Picture them as colossal time shapers, each one remixing the universe's tempo in its own style, each one proving that the flow of time is as varied, intricate, and surprising as the galaxies that fill the sky. Imagine drifting into a galaxy cluster, one of the universe's grandest gatherings, a gravitational convention where hundreds or even thousands of galaxies sit together like guests at an ancient banquet. If individual galaxies are solitary cities floating in cosmic darkness, then a galaxy cluster is a sprawling metropolis, humming with activity, layered with structures, and saturated with gravity so deep and complex that time itself has to tiptoe carefully through it. This is not the quiet, steady gravity of one galaxy pulling inward. This is the combined weight of entire celestial kingdoms piled on top of one another, creating a gravitational environment so intricate that time becomes tangled in ways it never encounters elsewhere. To enter a galaxy cluster is to step into a region where gravity does not come from one direction or one source or one center. Instead, it oozes from everywhere. Every galaxy contributes its own gravitational pull. Enormous clouds of hot gas, hotter than the cores of many stars, float between them, adding more mass to the mix. Even the dark matter, the invisible scaffolding that holds the cluster together, presses its weight onto space-time. You can picture the cluster as a gigantic bowl, except the bottom is uneven, dented, and rippling from countless overlapping sources of gravity. Time, wandering through this bowl, cannot help but slow, speed up, slope sideways, or drag slightly depending on where it happens to be. Now imagine yourself as a traveler sailing between the galaxies inside this cluster. At one moment, you glide near a massive elliptical galaxy whose weight pushes space-time downward with the confidence of an emperor claiming new territory. Time in this region moves more slowly. Your onboard clock barely notices the shift, but the universe does. Moments stretch, seconds lengthen. Even the flicker of your ship's instruments obeys this dragged-out rhythm. Yet nothing feels strange because you are immersed inside this slow-flowing pocket of time. It is like being underwater. Everything moves differently, but you only appreciate it once you break the surface. Then you drift farther outward, leaving the galaxy's dominating presence behind. You enter a region where galaxies are more spread out, where gravity's pull is gentler. Here the fabric of space-time rises like the slope of a hill. Time begins to quicken. Your seconds become slightly shorter, still normal to you, still familiar, but speedier compared to the deeper gravitational valleys behind you. Moving through these regions is like hiking across shifting terrain. Time does not flow along one smooth path. It adjusts to every gravitational contour underfoot. But the magic of galaxy clusters is not found simply in these deep and shallow zones. It emerges from the way the different gravitational fields overlap. Picture two enormous galaxies drifting past each other within the cluster. Their gravitational bowls meet, merge, and distort each other. Where they overlap, space-time stretches into forms that resemble saddles, dips, or ridges, shapes that change the flow of time in subtle, unpredictable ways. You might float into a region where two gravitational pulls partially cancel each other, lifting time into a slightly faster pace. Farther along, the pulls might amplify one another, pushing time into a slower drift. This makes traveling through a galaxy cluster feel like wandering through a time-bending labyrinth. Every region writes its own version of the temporal rulebook. Time might run a little slower near a dense knot of dark matter. It might run a bit faster at the edge of a long filament of gas. It might tilt off rhythm near overlapping gravitational wells, the way music from two distant rooms creates a strange shifting beat in a hallway between them. The effect is never dramatic enough to shock the traveler. There are no slow motion scenes, no sudden leaps forward, no eerie pauses. Instead, the differences are subtle, whispers, not shouts. But these whispers accumulate, revealing that a person living in one part of the cluster could experience a slightly different timeline than someone living thousands of light years away within the same cluster. Their clocks might drift apart over millions of years, not because either one is broken, but because time itself is obeying the gravitational geography around them. The strangest part emerges when you imagine a galaxy cluster as a story of collective mass. Each galaxy inside it is already a sculptor of time, bending moments within its own borders. But in a cluster, all these sculptors work together. Gravity from galaxy A nudges time in one direction. Gravity from galaxy B stretches it in another. The dark matter halo binding the whole cluster tightens the fabric even further. The hot gas between galaxies adds thickness to the cosmic quilt. Time is not shaped by one force, but by a committee notorious for poor communication and overlapping decisions. And then there is the sheer scale. In a cluster, light itself trudges through the warping of space-time, arriving bent and stretched, carrying with it not just images of distant galaxies, but the imprint of the time distortions it encountered along the way. To astronomers, those distortions act like fingerprints, subtle clues about where gravity is strong, where mass is hidden, and how time flows across different regions of the cluster. For a traveler drifting through this colossal structure, time becomes a companion that changes mood depending on the company it keeps. It is slower near the giants, steadier among the smaller galaxies, tangled near overlaps, and slightly quickened in the open spaces between. A galaxy cluster is not just a gathering of galaxies. It is a vast, shifting landscape where time bends, folds, and adjusts itself, quietly responding to the chorus of gravity surrounding it. And in this immense cosmic metropolis, time reveals one of its most remarkable traits, that even across billions of stars, trillions of planets, and unimaginable stretches of space, it never loses its flexibility. Every moment becomes a product of the environment, shaped not by a universal schedule, but by the rich, layered architecture of gravity in the universe's most massive neighborhoods. To understand time in the early universe, imagine waking up in the middle of a construction site where the building is not just unfinished, it is actively exploding into existence around you. Walls are forming, beams are flying into place, the floor is stretching beneath your feet, and an enthusiastic but slightly unhinged foreman is shouting instructions that contradict themselves every few seconds. That was the state of the cosmos in its first moments. time did not glide smoothly the way it does now. It stumbled, sprinted, hesitated, and behaved like a child let loose in a candy store, utterly overwhelmed, hyperactive, and uncertain about what direction to run. Right after the Big Bang, the universe was unimaginably dense and blisteringly hot. Not hot as in summer sun or volcanic lava, hot in a way that makes those temperatures look like lukewarm bathwater. Everything was squeezed together so tightly that space had no room to breathe. In those first fractions of a second, the laws of physics were still sorting themselves out, like new employees awkwardly learning their roles. Space was expanding faster than thought. Energy was everywhere at once, and time was trying its best to keep track of events in an environment where events barely had room to exist. In this early epoch, time flowed differently because space-time itself had not settled into the calmer, stretched-out shape we know today. Time, being welded to space, had no choice but to follow along with the chaos. Imagine trying to walk normally across a trampoline while 10 people are jumping on it. That was time in the beginning. Every attempt to flow forward was jolted by the violent expansion, by waves of energy, by fluctuations that made the entire fabric of space-time ripple like a kicked pond. During the earliest stage, known as the inflationary period, the universe expanded at a speed so wild that even light could not keep up. Distances ballooned outward exponentially, as if space were being inflated by a cosmic air pump set to maximum power. And because time is bound to the geometry of space, this explosive growth reshaped the way time unfolded. In some regions, the rapid expansion stretched time like taffy, making the passage of moments feel longer relative to regions where expansion slowed slightly sooner. In other regions, time moved more briskly because the density of energy was beginning to thin out. These differences were tiny at first, mere whispers, but they planted the seeds for uneven flows of time later on. As the universe continued to evolve, it cooled, not calmly, but like a pot of boiling water suddenly taken off the stove and tossed into the snow. The cooling process released energy in bursts, forming particles in waves. First, the most fundamental bits of matter, then combinations of those bits. Every time energy condensed into matter or matter annihilated back into energy, time's flow shifted slightly because the density of the universe changed. The denser the region, the slower time would run. And the early universe was a champion of density changes, swinging between extremes faster than a beginner trying to learn how to drive a manual transmission. To picture the effect, imagine two regions of the early cosmos, one where matter was momentarily clumped more tightly, and one where it was slightly more spread out. The first region bent space-time more deeply, slowing time's progression. The second region, being a little roomier, let time tick more freely. These differences were microscopic, but across cosmic scales and countless interactions, they created ripples that influenced how the universe grew. In a way, the earliest tiny disagreements in the pace of time contributed to the differences we now see between galaxies, clusters, and the vast voids that separate them. Time, without meaning to, helped sculpt the unevenness of the universe. As the universe expanded further, particles began forming stable structures. Quarks joined to form protons and neutrons. These bound together into atomic nuclei. Later still, electrons cooled enough to join those nuclei, creating the first atoms, mostly hydrogen and helium. Each phase nudged time's flow differently because each step changed the gravitational and energetic environment. When light finally escaped from the fog of early matter, filling the universe with the faint glow we now call the cosmic background, time began flowing in a way more recognizable to what we experience today. It was still influenced by density and gravity, but it no longer struggled against a backdrop of rapid-fire transformations. But the memory of those early distortions never disappeared. They are recorded in the temperature ripples of the background radiation, tiny variations that reveal where time once moved a hair slower or faster. They are recorded in the distribution of matter across the sky. They are even recorded in the large-scale structure of the cosmos, whose filaments and voids trace the echoes of the earliest differences in how fast moments unfolded. To appreciate how dramatic this era was, consider that the passage of time then was not governed by the familiar rhythms of stars and galaxies. They did not exist yet. It was shaped by pure energy, raw expansion, and the struggle of particles trying to find stable relationships. Time was negotiating its flow moment by moment, adjusting to a universe that changed more in 1 second than it changes today in billions of years. If the modern universe is a calm, aging ocean, the early universe was a whitewater rapid, roaring, unpredictable, and constantly reshaping the experience of time. And yet, out of that chaos, emerged the cosmic timeline we now follow, a timeline smoothed by expansion, cooled by distance, and shaped by the earliest, wildest variations in how moments unfolded. In that sense, time in the early universe was not just different, it was the foundation upon which every later moment, including this one, quietly depends. Imagine waking up in a universe where the word moment doesn't mean what you think it means. A moment for you might be a breath, a blink, a pause before answering a question. But somewhere else, far across the cosmos, there could be beings for whom a moment is an hour, or beings for whom it is 1,000th of what you experience. If time flows differently in different regions of the universe, then the creatures shaped by those regions would evolve with senses, instincts, and worldviews that fit their local tempo. Their version of normal time would feel perfectly ordinary, yet wildly alien to us. Start with a species that lives deep inside a region of strong gravitational influence, somewhere where time runs notably slower than it does here. Not catastrophically slow, not frozen in place, but slow enough that each second in their world holds more weight. Their entire existence would unfold in elongated slices of time, movements that we consider quick, like a bird darting across the sky, might appear to them as something between a blur and a disappearing act. Their conversations might be deliberate, measured, and paced with intervals that feel like slow breathing to them, but like vast silences to us. If we tried speaking to them, we would probably overwhelm them instantly. Our words would tumble out at a pace that feels frantic from their perspective, like trying to interpret instructions shouted through fast-forward playback. They might perceive our behavior as impatient or chaotic, not because we are, but because the very rhythm of our time is out of sync with theirs. We would be the hummingbirds of the cosmos, tiny, rapid, startling creatures that make them blink in confusion. Their world might reflect their time flow as well. Plants might unfurl leaves with exquisite slowness, each motion stretched into graceful arcs that take hours or days. Weather patterns might evolve in languid sweeps. Even simple gestures like turning their heads would look strangely drawn out to visitors accustomed to quicker time. Yet for them, it would all feel natural, a pace shaped by the physics of their homeland. Now imagine another species on the opposite end of the cosmic spectrum, flourishing in a region where time moves faster. Their seconds are shorter than ours. Their pulses race at speeds that would leave us dizzy. For them, the universe is a rapid-fire sequence of sensations and decisions. Their conversations might resemble strings of thought flickering like sparks. They might complete tasks in what, to them, feel like reasonable intervals, but to us appear almost instantaneous. To these quick-time creatures, we would look impossibly slow. Watching a human blink might feel like observing a heavy door inch its way closed. Waiting for a human to finish a sentence might feel like waiting for paint to dry. Our emotional responses, which we think of as quick, fear, surprise, laughter, might strike them as glacial. They might lose interest before we finish a greeting. Interacting with us might be like trying to communicate with a mountain, earnest, patient, but painfully slow-moving. Their world would be full of phenomena that unfold too quickly for us to apprehend. Their ecosystems might change rapidly. Their weather could evolve over time, frames that feel like instant transitions. Even their perception of danger and safety would hinge on rapid evaluation. Their instincts might require processing complex information in fractions of our seconds. To them, reacting slowly would be a luxury they could not afford. Now consider what would happen if two such species, one from slower time, one from faster time, met each other. Conversation would be nearly impossible. The slow time beings might feel overwhelmed, while the fast time beings would feel trapped in a universe running at a frustrating crawl. Emotionally, mentally, physically, they would occupy different realities shaped by the tempo of their timelines. But it becomes even stranger when you think about how these creatures might view the cosmos itself. A slow-time species might watch stellar events unfold at speeds that seem shockingly fast. A star's momentary flare-up might look like an abrupt flash, a sudden burst rather than a drawn-out astrophysical process. Planetary motion might appear too swift to track comfortably. The universe might seem unpredictable simply because time around them flows differently. For fast-time creatures, the universe might feel serene. Stars evolve on scales so enormous that these creatures might perceive the cosmos as stable, calm, and unchanging. Their own rapid lives could fit entirely within what we consider trivial cosmic intervals. They might be fascinated by slow processes like continental drift or orbital shifts, treating them as long-term mysteries rather than ordinary background events. Even their internal perception of life would differ. A slow-time species might experience emotions deeply because each emotional moment stretches into meaningful length. A fast-time species might feel emotions intensely but fleetingly, like sparks that burn bright and vanish. Their memories might be shaped by this quick pace, vivid, numerous, but short-lived. And then there is the question of consciousness. What would thought feel like in slower or faster time? Would slow-time beings savor each idea as though living inside a lingering note of music? Would fast-time beings think in bursts, 1,000 thoughts racing through their minds before we finish forming one? These differences raise one final speculative idea. Perhaps time itself helps carve out how reality feels to any creature. Not by changing the laws of physics, but by changing the pace at which those laws are experienced. Time may be the invisible architect of perception, shaping the cadence of life, thought, emotion, and awareness. If the universe contains regions where time flows at different speeds, and life somehow arises in these places, then the cosmos could be filled with beings who inhabit profoundly different realities. Not separate universes, but separate tempos of the same universe. Creatures whose lives unfold to rhythms we cannot easily imagine. Creatures who would look at us with the same bewilderment we would offer them. And somewhere out there, in some quiet corner of the cosmos, time might be shaping minds in ways we have yet to dream, teaching them a form of reality tuned to a tempo all their own. By now, we have wandered through a universe where time refuses to behave like a polite, consistent rulebook, and instead dances, drifts, stretches, slows, bends, loops, and occasionally sulks in a corner, depending on where it has been placed. And maybe the most astonishing part of this cosmic tour is not the strange behavior of time itself, but the realization that we humans, small creatures on a small world orbiting an average star, are capable of noticing any of it at all. Somehow, out of all the possible quirks the cosmos could have handed us, we received the ability to question the very thing that makes our lives unfold, the flow of time. Understanding the uneven pace of time does more than satisfy curiosity. It gives us a new lens through which to see ourselves. It tells us that our experience of time, the steady ticking of clocks, the familiar beat of heartbeats, the rising and setting of the sun, is not universal. It is local. It is personal. It is the universe's way of saying, here, in this place, this is how life unfolds. That realization can be oddly comforting. It means we are not living in a simplified, watered-down version of reality. We are living inside a perfectly valid slice of a much larger, richer, more flexible tapestry. Think of all the different environments we have explored, the monstrous gravity of collapsed stars, the swirling grip of rotating bodies, the gentle height-based shifts in gravitational potential, the cosmic stretching that separates galaxies, the hidden mass-shaping galaxy clusters, and even the early chaos where time stumbled its way into existence. These are not remote curiosities. They are reminders that the universe is a place where rules are sculpted by context. Nothing exists in isolation. Everything, light, matter, movement, gravity, and yes, time, interacts with everything else. When you realize this, the universe stops feeling like a static stage and starts feeling like a living, evolving structure. You begin to see that time is not a background setting. It is an active player woven into the universe like thread in a quilt. The deeper you look, the more you see how adaptable and responsive it is. It stretches when space stretches. It bends when gravity bends. It drags when mass spins. It slows when matter crowds together. It speeds when gravity lets go. Time is not a dictator. It is a collaborator, constantly adjusting to the shape of reality. And where does that leave us? It leaves us in a humbling, beautiful position. We are creatures who evolved in a region where time behaves calmly, gently, predictably. We never feel its distortions directly, and yet we discovered them anyway. We learned that we age at slightly different rates depending on how high we stand on Earth. We learned that fast-moving objects experience fewer moments. We learned that clocks near massive objects tick reluctantly. We learned that the early universe sculpted the first variations in time that shaped everything we see now. Each discovery is a reminder that the universe is far more layered than our instincts suggest. There is something profoundly poetic about recognizing that time itself has a history, that the universe has spent billions of years shaping the tempo of existence, and that tempo changes from place to place. It makes the cosmos feel less like a cold expanse of stars and more like a symphony where each region plays its own rhythm. Some parts keep slow, deep beats. Some parts flutter with fast tempos. Some improvise wildly. Some barely tick at all. And we, tiny observers sitting on a rock in a quiet arm of a spiral galaxy, have become aware of this symphony. We have learned to measure it, map it, and imagine scenarios where life might evolve under entirely different musical styles of time. The universe is vast beyond comprehension, yet here we are, listening for the patterns. Understanding the uneven pace of time also changes how we think about ourselves. It reminds us that our perspective is not the default one, it is simply ours, shaped by our gravity, our motion, our environment. If we had been born near a denser star, we would have lived inside slower time and never questioned it. If we had evolved in a region of thinner space-time, we would have experienced faster time and thought nothing of it. The fact that our world sits in a sweet spot of calm, steady time is one of countless coincidences that make life possible. Yet the most moving part of all this is not the physics. It is the meaning we attach to it. Knowing that time behaves differently across the universe gives us permission to wonder, to imagine, to question how small or large our place truly is. It suggests that our understanding of reality is always evolving, always expanding, always stretching outward like the cosmos itself. Instead of shrinking our significance, these discoveries deepen it. They show that we are participants in a universe filled with stories, each told by the flow of time in its own region. And perhaps that is the ultimate reflection. Time is not just something we move through, it is something we share with the universe. Our seconds, our hours, our lifetimes, they are chapters in a story shaped by cosmic forces far beyond our senses. We may be small, but we are woven into the same fabric that bends near stars, stretches between galaxies, and remembers the universe's first breath. The uneven pace of time does not diminish our place in the cosmos, it enriches it. It reminds us that we live in a universe that is dynamic, layered, and endlessly fascinating. A universe where even something as familiar as time still has secrets left to reveal.